Earth, a 4.5 billion-year-old planet still evolving. As continents shift and clash, volcanoes erupt and glaciers grow and recede. The Earth's crust is carved in countless, fascinating ways, leaving a trail of geological mysteries behind. So, investigates one awesome hole that shapes the Earth. It's extraterrestrial. It doesn't happen over millions of years, but in seconds. It's a force caused by an immense impact from asteroids. Giant rocks from space. The investigation of asteroid strikes has given scientists insight into the formation of the universe, providing a window into planet Earth's ancient past. There's a giant hole in the Arizona desert, 35 miles east of Flagstaff. It's huge, 3/4 of a mile wide and 550 feet deep. The Washington Monument could fit inside it. Confronting geologists in the late 19th century was, how did this happen? People agree that only a massive force could have created such a huge chasm. But what was this force? The most likely theory is that huge volcanic explosion had ruptured the rugged landscape. Scientists have discovered similar-sized craters in volcanic areas before. But Grove Gilbert, chief geologist for the U.S. Geological Survey, had another idea. After observing craters on the Moon through his telescope, he saw similarities between the Moon's craters and a mysterious hole in the Arizona desert, leading him to speculate that the Arizona crater might have been caused by an asteroid impact. But this was just a theory at the time. No one had proven that any crater on Earth had been caused by an asteroid. So in 1892, Gilbert decided to travel to the mysterious Arizona crater. He wondered if this could have an impact origin, or alternatively a volcanic origin. And so he had these two competing hypotheses that he wanted to test. Gilbert assumed that if the crater was caused by an asteroid, he should find a giant alien rock in the middle of it. But there was none. But he did see what he thought were signs that a volcano might be the cause. When Gilbert arrived, he realized that this hole in the ground was associated with some volcanic peaks. It didn't. You can see them in the background over the rim, or beyond the rim of the crater. And so immediately I think he was prejudiced, if you will, towards a volcanic as opposed to a meteoritic origin. Not far from the mysterious crater, Gilbert found another similar giant hole. He declared this one as an unusual volcanic crater, called a maar. He knew that 4 years before in Japan, scientists had witnessed the formation of a maar after a huge underground explosion of steam. The resulting crater resembled a giant hole Gilbert came across in the Arizona desert. They are produced when the Celtic magma rises through the Earth's crust, encounters groundwater, creating a steam explosion, which causes a blast that produces craters like the one over my shoulder. Intriguingly, the two almost identical craters were only 50 miles apart, in the same desert. One was known to have been caused by an underground steam explosion. Because of their close proximity, Gilbert concluded that the mysterious crater was also caused by volcanic activity. In 1896, he published his findings in an influential report, and for the wider geological community, the debate was resolved. But 6 years after Gilbert's findings, American entrepreneur and mining engineer Daniel Barringer arrived on the same scene. He was intrigued by mysterious small iron rock shepherds had found around the crater while grazing their herds. Barringer was convinced that Gilbert was wrong about the crater's origins. I'm holding in my hands a fragment of what started it all. It's not the type of material that one finds in any other geological, or created by any terrestrial geologic process. Iron and rock is usually mixed with other minerals. But at the mysterious crater, the iron was almost pure. And there are mountains, normally not found on the Earth's surface, spread over a huge area surrounding the crater. The pieces found here were meteorites, small rocks that form when big asteroids break apart. He had a hunch that this huge hole in the desert was formed by a giant asteroid, made largely from iron. Barringer immediately saw the commercial opportunities. The crater he calculated the asteroid must have weighed 10 million tons. At $80 a ton, Barringer he could become a rich man from mining the iron. So in 1903, Barringer bought the crater site of over 12 acres and hired crews to begin digging. Convinced with impact site, he named it Meteor Crater. We're in one of the remnants of Barringer's mining camp. This is a place where his miners lived. 8 slept while they looked for the buried mass that they thought was beneath the floor of the crater. For years, Barringer and his men found only small fragments of iron. They kept digging deeper shafts into the earth, the largest of which, the main shaft you can see, is a white island of debris in the center of the crater. And in fact, one of those holes close to me here reached a depth of nearly 14 feet beneath the surface of the earth. In all of these cases, or most of these cases, they found telltale hints of the impacting meteoritic body, but no giant mess. Barringer did stumble across some clues, however. Strange and unique rock formations, such as fine pulverized rock spread around the crater. He noticed quite rightly that it is so fine. It is almost like talcum powder. The type thing that immediately alerted him to something unusual in the geologic processes that shaped the land here. To Barringer, the pulverized rock was a major clue that pointed to one thing: the violent impact of an asteroid. As a geologist, I saw this rock. Okay, this is not something that I see around a volcanic crater. There's something going on here, and I need to figure it out. Barringer also discovered other oddities. At the crater rim, he noted a bed of rocks that were chaotically overturned. Dramatic energy uplifted the rocks. It rolled all behind me. Originally, they were absolutely horizontal, and you can see that they are tilted upward. And if you look very closely at the very top of the rim, they are completely overturned. For 27 years, Daniel Barringer obsessively sunk mining shafts in search of his giant iron asteroid with no success. Barringer died in 1929, having lost $600,000 of his own and investors' money, $10 million in today's dollars. The privately owned crater has remained his family to this day. His theory about the asteroid impact at Meteor Crater spurred further investigation based on 3 clues he had uncovered. The first, the pieces of pure iron scattered across the crater. Next, rock that had been crushed into fine powder. And finally, strange rocks thrown up and flipped over at the crater's rim. Interestingly, even though Barringer hadn't convinced the geologic community about the impact origin of this crater, he had launched at least a small number of people into an investigation of impact processes. Proof of Barringer's asteroid theory would get a boost some 6 decades later from an unexpected source. Meteor Crater was still a mystery to the geological community on whether it was caused by volcanic activity or an asteroid impact wasn't resolved until 1960. A young geologist, Eugene Shoemaker, became interested in Beringer's research. He would take the investigation in a new direction, which turned Meteor Crater into one of the most investigated crater sites on Earth. Shoemaker was working on craters left by nuclear explosions on test sites in Nevada. His task was to find out how the explosions transformed the landscape. Intriguingly, at the test sites, he found the exact same rock formations Beringer described at the mysterious meteor crater in Arizona. Shoemaker passed away in 1997, but his wife, astronomer Carolyn Shoemaker, recalls his findings. Gene compared meteor crater with the craters that he had been mapping at the Nevada test site. At the test site, Gene saw overturned beds, also near the top of the craters, in the rims, and that certainly told him that there was a strong similarity, because they were so obvious. At meteor crater, Shoemaker came upon another important clue that linked the Nevada test sites to meteor crater. He found samples of this very unusual rock. This was once sandstone, but he recognized it had been altered. The crater left by explosions from nuclear bomb testing. Shoemaker discovered crystalline structures, the same structures found at Arizona's meteor crater. Today we understand that this is shock sandstone glass. That is the original sandstone. All the quartz crystals were melted and put into a frothy, bubbly glassy matrix, which we have here. They were caused by the incredible energy released in the shock waves of a nuclear blast. For Shoemaker, it was conclusive proof. The vast meteor crater wasn't formed by volcanic eruptions. Instead, it was created by a powerful asteroid impact in just a split second. The shock rock also gave scientists a clue about the age of the crater. When an asteroid hits the Earth, energy blast is absorbed by the surrounding rock using a process called thermoluminescence dating. Scientists are able to measure the amount of energy the rock is giving off in the form of light. The shock rock of meteor crater told them that the impact happened 50,000 years ago. But for some, there remained one problem with this theory. If the Arizona Earth was crushed by a huge asteroid, where was the rock that made the impact? Scientists had a hunch that when it struck, the iron meteorite had vaporized. Inclusive evidence came in 1997, when scientists were able to simulate the impact using advanced computer modeling. From the side of the crater, they calculated that the asteroid must have weighed at least 300,000 tons when it struck. The data further revealed that it hit Earth at a speed of over 25,000 miles per hour. That's 35 times the speed of sound. Upon impact, the asteroid triggered a massive shock wave, many times more powerful than a nuclear explosion. Within a matter of seconds, this impact crater behind me was excavated, and this debris was a deposit on the landscape. Within seconds, the shock wave and a very high-velocity air blast radiated across the landscape. The shock wave traveled back up from the asteroid's iron core, vaporizing most of it and scattering the rest in small pieces over a wide area up to 6 miles away. The energy that produced this crater ranges somewhere from a few hundred to perhaps 1,000 times greater than the energy that destroyed the city of Hiroshima and Nagasaki in World War II. The investigation has uncovered reasons why there are no big remnants of asteroid rock in the Arizona crater. Crystal structure in the rock showed evidence of a strong shockwave that followed the impact. Computer modeling revealed that the speed and size of the asteroid created enough energy for the rock to vaporize when it hit. This crater is particularly important because it is the youngest and most pristine impact crater on the surface of the Earth. It was also the first recognized impact crater on the surface of the Earth, and so it is in some sense the Rosetta Stone. It is the touchdown for geology. It is here that specialists from around the world come to study and learn about impact cratering as a geologic process since 1960. Gear proved that meteor crater was an impact site. Geologists went looking for more, armed with some information and the developments in space and satellite technology. They'd revolutionize us, our understanding of how asteroids have shaped the surface of the Earth. Once the meteor crater in Arizona proved an iron mass can burst from space and create a monster chasm, scientists began to search for others. They questioned whether some craters they thought of as volcanic were, in fact, caused by asteroids. The investigation turned to Sudbury in Ontario, Canada. There's no obvious crater, but for over 150 years, the city has been the center of fabulous mining wealth and a geological mystery. 3,000 feet below ground in one of Sudbury's mines, thick veins of copper and nickel are on view. Until recently, these mining riches were associated with volcanic activity. One of the real distinctive features of Sudbury is the fact that it has world-class metal deposits associated with it. Really, these were thought to be related to volcano activity and magmas coming from inside the Earth, bringing ore metals from the inside out. But something didn't add up. When scientists investigated the rocks around the mine, they were surprised. None of the outcrops were typical of the types of rock created by a volcano. To geologists, it was a hint that the copper and nickel treasured below the surface were formed by a different process. They were stumped until it came across Eugene Shoemaker's work on meteor crater. It made them wonder whether this vast mine could also have been formed by an asteroid impact. Could the vast reserves of copper and nickel have arrived from space? Rocks above ground reveal new evidence. What we have is a conical type fracture system, with these lineations or lines running through them, and they focus down into a point. These deformed rocks are called shatter cones. Spread's convinced that the only force powerful enough to deform a rock into a shatter cone like this would be an asteroid impact. And these are formed due to the shock wave interacting with the target rocks. And they compress the rocks just like a compressed spring. And then the shock wave releases. They form these honeycomb structures, which are beautifully shown here. So they are diagnostic of impact. We can't form them any other way. You can't form them with dynamite. You can't even form them with nuclear weapons. But shatter cones were only a hunch. Another clue came from the composition of the rock. It's a mixture of violently broken pieces, fused into melted material. So what we have here is made up of the debris from the Earth's crust, blasted into millions of pieces, and the darker core material may well contain traces of meteorite, left in it in the form of iridium. Iridium is one of the rarest metals on the surface of the Earth. In space, it is 1,000 times more abundant. Asteroids are like space rubble, and their composition varies dramatically. Some are made of rock-like material, some from metals such as iron. But they all have one thing in common. They all contain comparatively large amounts of iridium. So any high amounts of iridium found on Earth becomes a fingerprint of an impact event. So what we're going to do is take a sample and analyze it to see if we can find an enriched iridium signature. It would tell us how we have a particular class of meteorite